This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and the scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form BC, Question 2. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form BC Question 2 involves a particle moving in the plane. Its position is given by a vector-valued function, x of t, y of t, at time t, where t is measured in seconds, and x and y are twice differentiable functions, both measured in meters. We are given a symbolic expression for the derivative x prime of t, and we also have selected values of y prime of t given in the table. And in addition, we know that the position of the particle at time t equal 12 is 4 minus 3. In part A, we need to find the speed of the particle at time t equals 6. Now, the key concept here is, of course, speed. Well, that is, how to find the speed of a particle moving in the plane at any time t. Now, I'm going to talk about this concept in the context of a vector function. One of the most important definitions in any mathematics class is that of a function. And we know that a function is a rule that assigns to each element in the domain a unique element in the range. A vector-valued function, or just vector function, is simply a function whose domain is a set of real numbers and whose range is a set of vectors. So this problem involves a vector function whose values are two-dimensional vectors. There is a close connection between vector functions and particle motion. Suppose a particle moves in the plane so that its position at time t is given by these parametric equations. If we consider the vector function r, then r of t is the position vector of the point P. Therefore, any continuous vector function r describes the motion of a particle in two dimensions, and it also defines a curve c that is traced out by the tip of the moving vector r of t. The derivative r prime of t of a vector function r is defined in much the same way as for a real-valued function. As a result, if we write r of t like this, then here's an expression for r prime of t. We simply take the derivative of each component. If a particle moves along a curve so that its position vector at time t is r of t, then the velocity vector v of t is given by this expression. And finally, the speed of the particle at time t is the magnitude of the velocity vector. Therefore, the speed of the particle is given by this expression. Let's use these ideas to find a solution for part A. Looking ahead, and knowing the expression for the speed of a particle, I'm going to start by finding x prime of 6 and y prime of 6. We're given an expression for x prime of t, so I'll use this to find the value of x prime of 6. The value is 6 divided by the square root of 61. I'll use the table of values given in the statement of the problem to find that y prime of 6 is equal to minus 2. And now I'll use these values in the expression for speed. Here's the expression for the speed of the particle at time t equals 6 seconds. Next, use the values for x prime of 6 and y prime of 6. And finally, a little simplification. Note that this problem asked for the answer with correct units. So speed is the magnitude of the velocity, and the units for velocity are meters per second. Here are the scoring guidelines for Part A. This problem was worth 2 points. The first point is for presenting a correct expression for the speed of the particle at time t equals 6 seconds. And the second point is for the correct answer with the appropriate units. Here are some interpretations of these guidelines to help understand how points are earned and to help prepare for the next AP Calculus exam. The first point is earned for an expression for speed applied to our problem. That is, the point is not earned for a general formula for speed. Here are some example student responses and how each is scored. This response is a general expression for speed. It's not applied to our problem. So no points are earned yet. The student could, of course, go on to use this formula in the context of our problem and earn points. In this example, the student has added at time t equals 6, and so they have applied the general formula for speed to our problem. So this earns the first point. And this expression is the formula for speed applied to our problem, and it also earns the first point. Note that the student could certainly use Leibniz notation in this problem also. The second point is earned for the correct numerical answer with the correct units. Now, let's assume that students have access to their calculators for this problem, as they did for all problems on the 2020 AP Calculus exam. So a numerical answer of 2.142 truncated or 2.143 rounded with correct units earns the second point. Here are a couple of example student responses. In this example, the expression for speed is correct, and we assume that the student used technology to arrive at the correct numerical answer, and the units are correct. So this earns both points. In this example, the use of the expression for speed is clear. It's applied to our problem. And the final numerical answers do not need to be simplified. So the units are correct. This earns both points. In part B, we need to find the x-coordinate of the position of the particle at time t equals 4. I believe the key concept needed here is net change in the context of the fundamental theorem of calculus. The definite integral as an accumulation function and the concept of net change are two very important ideas in AP Calculus, and they are often tested in problems in context. Let's start by recalling the fundamental theorem of calculus, parts 1 and 2. If f is continuous on the closed interval a to b, then if g is defined in this manner, then g prime of x is equal to f of x. And the definite integral of little f of x dx is capital F of b minus capital F of a, where capital F is any antiderivative of little f. Let's take a closer look at the fundamental theorem of calculus and think about this theorem in a certain context. The function g in the FTC depends only on the variable x, which is the upper limit in the integral. If x is a fixed number, then the integral is a specific number. If x varies, then the integral varies and defines a function of x denoted by g of x. If f is a positive function, then g of x may be interpreted as the area under the graph of f from a to x, where x is in the interval a to b. Therefore, I like to interpret g as an area so far or accumulation function. Note that if f is continuous on a to b, with positive and negative values, then the function g is really a net area so far function. The fundamental theorem of calculus also provides a simple method, well, simpler than evaluating a complex Riemann sum, for evaluating a definite integral. If capital F is any antiderivative of little f, then we can find the definite integral from a to b of little f of x dx by evaluating capital F of b and capital F of a and subtracting. We've learned that the derivative, capital F prime of x, represents the rate of change of y equal capital F of x with respect to x. And we also know that capital F of b minus capital F of a is the change in y as x changes from a to b. Now remember that y could, for example, increase, then decrease, and then increase again. And therefore, capital F of b minus capital F of a really represents the net change in y. So using this interpretation, the fundamental theorem of calculus part 2 can be restated in terms of net change. So here is what I call the net change theorem. The definite integral of a rate of change is simply the net change in the original function. Here's another way to interpret the definite integral from a to b of capital F prime of x dx. This definite integral represents an accumulation of the change in capital F over the interval a to b. And we can also rearrange the terms in the net change theorem to provide an alternate interpretation and a very useful approach for solving AP calculus type problems. Capital F of b equals capital F of a plus the definite integral from a to b of capital F prime of x dx. Or here's a way to interpret each of the terms in this expression. The end amount is equal to the start amount plus the net change. And if you think about it, this seems very reasonable. And note that we could also solve for capital F of a in this equation if we want. Let's use these concepts to solve this problem. First, I'll use the net change theorem with a equal 4, b equal 12, and I'll actually solve for x of 4. The value for x of 12 is given in the statement of the problem. And we also have an expression for x prime of t. Now, some students may correctly or appropriately use their calculator at this point, but I'm going to solve this problem analytically. To find an antiderivative, this is a pretty straightforward u substitution problem. I can just let u be equal to t squared plus 25. I won't go through this in detail. And in fact, I'm sure many of your students see this integral as almost inspection and can simply write a correct antiderivative without going through a u substitution. In either case, here's an antiderivative. And in this step, we use the FTC to evaluate the antiderivative. And a little simplification leaves me with the square root of 41 minus 9 for a final answer. This problem was worth 3 points. The first point is for using a correct integral expression on the way to finding x of 4. The second point is for using x of 12 in the expression for x of 4. And the third point is for the final answer. Here are some interpretations of these scoring guidelines. The student must present our definite integral to earn the first point, and that means they must include the limits. We often struggle with scoring responses that do not include the dt. Without a dt, the integrand can be ambiguous. This is a very informal guideline that we often use, that we've developed over the past few years. Now look, there's no guarantee that this will be used in future exams, but it does seem pretty reasonable, and it seems pretty fair to students. A missing dt in the integrand is assumed to appear at the right of the last term after each integral symbol and before any comparison symbol. And I'll show you an example of the use of this rule below. The second point is for using x of 12 in the expression for x of 4. Now, as you might expect, some students will omit this value and use only the definite integral. And finally, the third point is for the answer. This can be a numerical answer, rounded or truncated, and the units are not necessary here. In this case, we'll ignore any units that are presented by the student. Here are a couple of student responses and how each is scored. In the first example, the definite integral is presented correctly. I see the value of x of 12, and the final numerical answer is correct. This earns all 3 points. In this example, the integrand is ambiguous. I read this as if there is a dt after the 4 and before the equal sign. So I have to check the final answer, and it's correct. So I conclude that this is a presentation error. And I'll award this 2 out of the 3 points. We're stressing notation and good communication. And using this standard, this response cannot earn all 3 points. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts and a reasonable expectation of how they would be scored. We'll look at more parts of this free response question in the next video.